Ladies and gentlemen, what's up? Here we go, on to chapter 10. And so you think you know something about circles, do ya? Well, here's the scoop, just to give you a little inside scoop. We're going to talk about these things called seek. Yeah, it actually stands for secant. What? Inscribed angles, secant angles, chord angles, secant tangent angles, things called arcs, things called tangent angles. It sounds like I'm stuttering, but I'm not. These are all different things that we're going to talk about in this particular chapter. And here's what's even cooler. Let me give you a little inside scoop about what you're going to be doing. Can you find the measures of all 18 angles and 7 arcs? You read it correctly. That's a lot of angles and that's a lot of arcs. Here's the picture. Oh boy. Check that picture out. There's the 18th angle and there's a ton of different arcs on there. And I know you're thinking like, holy moly, roly polies. Yes, it will be possible, ladies and gentlemen. By the time that we're done with this chapter, actually well before we're done with it, maybe about 2/3 of the way through, you will be able to find the measure of all of these angles and find the measure of all these arcs, which is really, really cool. So just be patient, little ones. You'll be able to do it. So, on to the basics of circles. Now, what I want you to do in your notes for section 10.1 is really what you're going to learn in this video is some as it says, the basic stuff. Basic definitions, basic terminology. But what I want you to do right now is at least understand this. What in the world is really a circle? Well, you can see this thing right here, BA, it is 5.26 centimeters, whatever. The definition of a circle is this. A circle is really just nothing more than an infinite set of points that are all equidistant from one fixed point. So say, for example, point B. That point B isn't going to move at all. It's going to stay fixed. But if I take this point A and I move it around and say I want to move it over here, watch. Whoa, sorry, wrong thing. Bing. So I'm going to stop it. So all of these things here are little dots that's being put down that are the same exact distance, 5.26, away from this point B. If I keep that point moving in the same distance from that center point, what you can see, it's laying down all these points that are the same exact distance from this fixed point B. And notice, yes, it's creating, a circle. So that's what a circle really is. It is a set of points that they are all equidistant from one fixed point. Now, here's a definition. Draw this thing in your notes. The center of the circle to the actual edge. That thing right there is called the radius. This thing here from edge way over here to edge, that thing right there, that is called a chord when it is a segment where the endpoints are on the circle. If you have a particular chord that goes across the actual center and crosses through the center of the circle, that thing right there is a center, and this chord, notice, crosses the center of the circle. That's called the diameter. So you got radius, which is really just from the middle to the edge. Diameter is the whole way across, but it goes through the center, so that's the biggest particular segment that you're going to find in the circle. And a chord is nothing more than a segment that goes from, edge to edge of the circle. So there's your basics, if you will, of circles and their definition. So let me pull this PowerPoint back up and give you another definition that you can write. This is kind of definition day number 1, if you will, of these circles. Definition here, when two circles are congruent. If they are going to be congruent, the only way that they would be congruent, as you remember from the entire year we've talked about so far with congruency, they have to be the same size and same shape. We're not talking similarity where they're just the same shape, because any circle is similar to any other circle. But when they become congruent, they're same size, same shape. And here's the only way that it can be done. If they have congruent circles. What did I just say? If they have congruent radii. So if and when you are asked to prove, what did I just say? Yes, you're right. You heard it. We're getting back into proofs a little bit. So I know, pause the video, do a quick little dance of happiness. What's up? But we're getting back into proofs. Oh yeah. So if you're going to be proving two circles are congruent, then you have to show that their radii are congruent. Or vice versa. If you know you have two circles and you say, hey, their radii are congruent, then that would imply to you that the circles are congruent. And you use that just like any other definition as your reason in a 2-column proof. So there's definition number 1. Definition 2 and 3. Sometimes people get confused and they don't know what the center of the circle is. Why is this dot in the middle? That is the center of the circle. And you actually use that center of the circle to name the circle. For example, they'll actually give you, let me do this. Should work. They can give you a letter here and say, hey, the center of the circle is A. Great. They'll call that circle A, like we've seen throughout many other examples. Okay? So what else is there? Well, you got the center of the circle, and then you got the interior of the circle. So when you see, a point is on the interior, it means it's somewhere in this blue shaded region. Not the center of the circle, but it's somewhere in the blue shaded part. So if that's the interior, then the exterior is all the stuff outside of it. Then that leaves the actual white rim around the circle. That is what's called on the circle. So if you have a point somewhere that is actually on the circle, then that point would be exactly right there on the rim of the circle. So if I had that as B, yeah. So this distance then from the rim to the center, that's your radius that we talked about just a little bit ago. So a point on the circle is that. Exterior of the circle is outside of it. Interior is, of course, inside of it. And then the center of the circle is the actual point right there that you use to name the circle. So there are some basics. Okay. Definition 5. This is kind of a cool one. 2 or more coplanar circles. Coplanar means on the same plane. So if we have 2 or more coplanar circles, kind of like all the ones you see here in the background of this PowerPoint, if they have the center that's exactly the same, they're called concentric circles. So that is your definition right there of concentric circles. And here's some examples. Yep, a bullseye. That, whether it's shooting a archery, or you're shooting out in the range with a rifle or whatever, or you're actually over here throwing darts, that is an example, 3 great examples of concentric circles. Because by definition, they are again 2 or more coplanar on the same plane circles that had the same exact center. So there you go. All the different little circles that you see, they're concentrics. Here's another one. If you dropped a particular drop of water in, a bigger thing of water, a glass or a pond or whatever, they create this ripple effect, but those circles are all concentric because they all have the same center. Cool. So there's concentric circles. Let's keep going. So next definition is something that you already know, but just to rebrief it. Yeah, that's right, rebrief. We're going to brief it, remind you of it. The area of a circle. Apple pies are squares, what I've always told you guys. Area equals pi r squared. The circumference of the circle is nothing more than cherry pie delight. So it's cherry pi delight, or 2 pi r. Again, I told you guys in class, don't remember it as 2 pi r because sometimes people get confused. My suggestion, remember it as pi times d. But remember, d is nothing more than just 2 times the radius anyways. Hence is why you got 2 and r in the other formula that you can memorize. Either way, cherry pie delight is an easy way to remember. Okay, definition 8. What is this thing called the distance that a particular chord is from the center? What? Well, it says the definition right here. The distance that a circle actually is from the center of the circle is the measure, so how far, the perpendicular segment from the center of the circle is to that chord. You're going to say, what are you talking about? Pause the video, get this definition down, because I'm going to turn to an example. So the distance that the actual chord is from the center of a circle. It's important to know because you're going to be asked that a lot. And there's going to be some theorems that come up and some other definitions throughout this chapter that talk about, and we use this idea of distance that a chord is from the center. Okay? So let me give you an example of that. So let me first of all, I'll pull this up, I'll draw a quick circle. So here's my circle. That's beautiful. So it's circle J. And if I draw a chord that goes across like this, well, if I want to know how far this chord is from the center, you don't measure the actual radius. No, no, no. That's not how far the chord is. The definition, as it says here, it is the distance from the center of the circle to the chord. That's what the actual distance is. That perpendicular segment. So, I'm talking gibberish. Hold on. Let me just show you. So, if I do this, if I draw this thing right down here perpendicularly to the chord, now we're talking this thing right here that I'm pointing at, that distance, however far NJ, New Jersey, however long NJ is, that is considered to be the distance that this chord is from the center. If I move it over here a little bit where it's not perpendicular, that's no longer considered the distance the chord is from the center. It has to be the perpendicular segment, yeah, that length right there to the chord. And we're going to use that again a lot, this concept of how far a chord is, because this distance determines many other things. And you're going to see in the next couple theorems, but you also see throughout many other theorems too. It determines a lot of other stuff. So anyways, there's that. So let's lead into the actual theorems that use this entire idea. So Theorem 74 says this. If a particular radius, and it's in quotes for a reason, you'll see here example why, but if a radius, or you might as well put this in your notes, it is in quotes because you can put, or part of a radius, so it doesn't have to be the complete radius itself. The example that I just showed you, this right here, is part of a radius. Because if I actually extended this thing across, whoops, it won't let me do it. If I extended this thing across over here, like that, that thing now is my radius. From point O over here to J, that's my radius. But nothing more than this NJ right there, that thing, that's just part of the radius. So that's why the theorem says if a radius, quote unquote, or part of a radius, is perpendicular to a chord, then it bisects the actual chord. And you're going to say, what are you talking about? Well, here's a scoop. Let me show you how that works. So if a radius is perpendicular to a chord, or part of a radius like you see in this picture, I'm going to take this radius, or part of a radius, and I'm going to make it perpendicular to the chord. Now you can see right here, as I move this, whoa, really move it, this thing here, I want it to say 90 degrees because I need ACD to be a 90-degree angle to make AC perpendicular to it. So as soon as I make that thing perpendicular to the chord, this theorem again saying, oh, it bisects it. Well, if that's the case, take a look. Bingo, it does. It makes this DC segment 4.4, and it makes CB 4.4 as well. As soon as I take this point and move it over here and make it not perpendicular, notice the segment's not bisected anymore. So that's what the theorem says. If a radius or part of a radius is perpendicular to the chord, bingo, as soon as it's perpendicular to the chord, it bisects it. Beautiful. Okay, so that's that theorem. The next theorem, Theorem 74, is nothing more than the converse of Theorem 74. I think I just said Theorem 74 twice. The Theorem 75, it is nothing more than the converse of Theorem 74. So it says, if a radius, or part of a radius, hence is why it's in quotes, of a circle bisects the chord, then it's perpendicular to the chord. Pause the video, get that written down. Here's the example. So if I have a radius that bisects a chord, so I want to make this particular radius, or part of the radius, make these two things equal. So I need to make sure that these two things are equal. There we go, 5.2 and 5.2. So this thing bisects this actual big chord. Then, as you notice, bingo, it's perpendicular to the chord. Again, it's nothing more than the converse. So if this bisects, great, then it's perpendicular. If this is perpendicular, great, then it bisects the chord. There you go, guys. There's your basic fundamentals in two theorems, Theorem 74 and Theorem 75. That's going to be used, and these definitions, yes, that's going to be used in proofs and many other questions throughout this section, of course, but throughout the chapter. So study this, go back and watch it again because that was a lot of information very quickly. And you'll want to watch it again just to make sure you got it all. So you guys are awesome. We'll see you in your class. Later.